Hey, Kenny's 320. So we have been talking about the respiratory system, and of late we've been talking about gas exchange. In this particular module, we are going to look at oxygen and carbon dioxide, but mostly oxygen exchange inside the muscle. And what this is going to lead to is a discussion about VO2, which we have talked about very generally. I've told you that it's the amount of oxygen that you take in and carbon dioxide that you put out. But we're going to actually look at the equation for it in this particular module. So like the bloodstream, we have this thing called myoglobin, which is inside the cell, which takes up the O2, and its structure is similar to hemoglobin, and it has an even higher affinity for O2 than hemoglobin. But the O2 myoglobin dissociation curve is shaped very differently. It's much steeper slope. The loading portion of the PO2 at the loading portion is going to be about 20 millimeters of mercury, and the releasing portion is going to be at about 1 to 2 millimeters of mercury. So let's just take a look at it. So this is our hemoglobin dissociation curve that we saw in our last mini lecture. Now, when we look at myoglobin, it's going to hold, and then suddenly it's going to fall off very quickly, and it's going to disassociate very quickly. Whereas you see it's a lot less steep in the hemoglobin dissociation curve. So we're going to get partial pressures that are much lower, and then it's going to desaturate pretty quickly. But again, the whole hope is to deliver this when the cell needs it the most. And of course, that's when there is less partial pressure of oxygen available. So what are the factors that influence O2 delivery and uptake? Well, we've already talked about a bunch of them already. So there's O2 content of the blood. So this is represented by partial pressure of oxygen and hemoglobin percentage of saturation. And this creates arterial PO2 gradient for tissue exchange. Okay, so remember, we expect that your PO2 gradient is going to be highest at the lungs, and then as you get closer to the exercising muscles, there's going to be this disassociation. Same is true with myoglobin. So if you have, but another factor could be blood flow. So if you have decreased blood flow, that means you have decreased opportunities to deliver the O2 to the tissues. And you know that exercise increases blood flow to the muscle. And then there's the local condition problems, the pH and the temperature ones. So you shift the O2 hemoglobin dissociation curve to the right, you decreases in pH, increases in temperature, promote unloading in the tissue. So all of these things are all factors of exercise, and all impact O2 delivery. So we know that as we pick up exercise, we're going to see that the delivery and uptake of oxygen is going to increase, right? So we have fixed principle, which we did talk about in previous lectures, but now we're going to put it to this. So VO2 is your cardiac output times your AVO2 difference. So again, if we're looking at this another way, VO2 is your heart rate times stroke volume times your AVO2 difference. And so we talked about AVO2 difference. So this is the difference of oxygen partial pressure on the arterial side of the muscle versus the venous side of the muscle. And so you get this AVO. So what is the difference between those two? And then you multiply that by your heart rate and your stroke volume. So what are the respiratory limitations to aerobic capacity, or VO2 max? Well, the reality is that the ventilations themselves, so the actual delivery of the oxygen is really not the problem, because the respiratory muscles are only about 10% of your VO2. So if you're talking about a VO2 of 30, then 3 milliliters of mercury, milliliters of oxygen per minute, and then 15% during heavy exercise, because they're so fatigue resistant. The diaphragm will go on and on and on forever. If you guys have done, I did marching band in high school. there's a lot you can do when you're relatively fit and your diaphragm is doing what it's supposed to. So airway resistance and gas diffusion usually not a limiting factor, though it can be in certain populations. So when could ventilations and diffusions become a limiting factor? Diffusing become a limiting factor? Well, as I talked about before, we know that the barometric pressure of the air is 760 milliliters of mercury at sea level. But look how drastic things change as you move from Miami to Denver to Mexico City to Pikes Peak at 14,000 feet, and of course at the level of Mount Everest, we're talking about 30,000 feet. Your barometric pressure is about 253 millimeters of mercury. Oops, sorry about that. So just not to mention that you have extreme temperatures, which again, core temperature, body temperature is going to impact your disassociation. But look at these partial pressures of oxygen just fall off down to 53. This is why most people and most smart people who travel to Everest, not that it's ever a super smart thing to do because it's exceptionally dangerous, have to wear oxygen, because there you have to create this partial pressure disparity so that you can take up the oxygen that you need, and so it will associate with your hemoglobin and so forth and so on. So really the only time that ventilations and diffusion would become a limiting factor is if you were exercising at altitude and your partial pressures and your barometric pressure changed that significantly. So this is what happens at the level of the muscle. Next time that we're getting together, we're going to put this all together and see what happens when we start to exercise. And just to be clear, this is why they have that. So when you think about the Olympic Training Center in Colorado Springs, Colorado, why would you want to train at altitude? Because you become very efficient at getting oxygen into the system, and most places that you compete at are sea level or below. So if you had a barometric pressure that you're accustomed to that was closer to 600 and then made your way down to sea level, you would suddenly be that much more effective. That's why they always use the expression train high, compete low. So train with an altitude that's high and compete at a low sea level altitude. I hope this makes sense to you guys. Make sure you check out the additional content, and I'll see you on the web.